Okay, welcome back. In the previous page, we have mentioned the Boolean models we can use for building both index as well as to answer queries. However, based on the previous example, we find that a Boolean model is very easy, also very straightforward, and it has many advantages. It can do the operations very fast. However, we also find some problems with the models we mentioned before. First of all, when we have lots of documents, and the document may also contain lots of words, lots of terms. If so, then this incidence matrix we mentioned before between terms and documents will be very large, and sometimes can be extremely large, right? Let's assume if we have the internet as all the documents, and the internet contains all the words in them, right? Then the incidence matrix for the whole internet for the search engine will be extremely large, which is almost impossible to handle them, right? Besides not just space for storing this incidence matrix, also this incidence matrix can also be very sparse, right? If you still remember, right, for the values inside this incidence matrix, it denotes this document contains some words. However, given a large amount of documents as well as terms, the incidence relationship between the documents and terms can be very sparse. In other words, inside this matrix, lots of entries will be zero values actually, which may create some problems for us to do the queries, right? Now, given two terms, we have their incidence vectors. However, inside them, lots of the entries are zeros. And when we do the Boolean expressions based on it, then the time cost will be very large, right? Because we have to scan the whole entries in it, even though not all of them are zeros. Then the question will be, given the two disadvantages we mentioned above, can we have a better solution for representing the term and document relationships? The answer is yes. We can probably only record the values, the entries with value 1s, right? In other words, given a term, we only need to record the documents contains it, right? We can ignore the remaining ones. What does this mean? So we can show an inverted index at the bottom. For the inverted index we are storing here, it is very different from the previous matrix we showed before, right? So in this inverted index, we have two main parts. The first part is called dictionary. It contains all the terms we plan to record in the index table. And following this dictionary, these terms will have this posting, right? This posting denoting the IDs of the documents contain this term. Now, given the bruters this term, we can have the posting, which will be a list. In this list, we have a bunch of document IDs which contain the bruters. Now, document 1 contains bruters, document 2 contains bruters, similar for document 4, document 11, and etc. So in other words, for each of the terms like T, we can store a list of all documents IDs which can contain the term inside it. In this way, given a term, we can access all the document ID contains it by following this dictionary as well as the arrows, right? So compared with the previous matrix, this inverted index based on the dictionary and the postings, it will be much smaller, right? Also, inside it, we only record the entries with value 1s we mentioned before. We only record the ID of documents which can contain these terms. In other words, this posting list of each term will be very dense, actually, compared with the previous matrix. It can save lots of storage space, as well as can help us access documents in a very fast manner. Okay, then the question will be, how can we construct this index, as shown here, containing both a dictionary as well as postings? So we show the procedure to construct this inverted index in this page. So given the documents containing all the words and terms, the first step we probably need to do actually is to connect all the documents to be indexed. Now we have lots of documents, right? And let's assume we have document 1, the first one, and document 2, and etc. We can connect all the documents and we can also assign them with one ID which is unique and different from each other. And in step 2, given the documents, we tokenize the text and turn each document into a list of tokens instead. In other words, we split these documents into tokens. The friends, rooms, and countrymen, they are all the tokens, similar for the remaining ones from other documents, right? So, and etc. And based on these documents as well as tokens, we can further do some linguistic pre-processing to produce a list of normalized tokens instead, which will be the index terms. In other words, for all the tokens, we can get their lowercase representations and also remove this s, for the ends of the tokens, right? Because their friend and a friend will treat them as the same token actually. So this can be done by some linguistic pre-processing steps very easily. And we can transform them into the index terms instead, like friend, room, countryman, so, and etc. So based on the tokens as well as document IDs, we will be able to index documents that each term occurs in by creating an inverted index instead. So this inverted index will consist of two parts: the dictionary of terms we mentioned here, right, as well as the postings of document ID will create in step 1. So in this way, we'll be able to construct an inverted index based on the documents. So in this inverted index, for each term, we will be able to point into a list of documents which contains it. Okay, so we have this inverted index. Then the next question will be how can we do the queries based on it, which is very different from the previous Boolean models, right? Here for the inverted index, like here, we can no longer do the Boolean operators based on them, because here the number we have here denotes the ID of the documents. They are no longer denoting the appearance, right, or the incidence relationship between document and terms anymore. Then the question will be how can we do the queries based on it?